This two type of brake pads come from completely different worlds, yet thousands of drivers bolt racing brake components onto their daily drivers, creating a dangerous mismatch that could leave them unable to stop when they need it most. Competition brake systems work only at temperatures that street driving simply never reaches, and this thermal gap affects everything from emergency stopping power to your wallet. Here's the fundamental problem. During normal street driving, your brake rotors and pads rarely climb past 400 degrees Fahrenheit. Even aggressive highway driving with heavy braking might push front brake temperatures to 600 degrees on a front-wheel drive car. But racing brake pads don't even begin working properly until they hit 500 to 800 degrees Fahrenheit, with many compounds needing temperatures between 1000 and 1500 degrees to deliver their promised performance. Take the Hawk DTC-80, a popular racing compound that generates nearly 0.7 coefficient of friction. That's double what even the best street brake pads achieve and triple the friction of average daily driver brakes. Sounds impressive until you realize these pads only work between 400 and 1600 degrees Fahrenheit. As one brake engineer puts it, most race pads don't wake up until 300 degrees Celsius. Until racing pads reach that temperature range, they're not just ineffective, they're actively damaging your rotors while creating excessive noise and dust. The physics reveals why this temperature dependency matters so much. Contrary to popular belief, a brake pad doesn't work by simply squeezing against a rotor. During the critical bed-in process, brake pad material actually transfers onto the rotor surface as it wears, creating a layer that provides the proper surface for friction generation. This transfer process and the resulting friction characteristics depend entirely on temperature. The very friction material creating heat gets directly affected by that heat, and racing compounds reach peak performance only at elevated temperatures that street driving cannot sustain. The temperature ranges tell the story clearly. Normal street driving keeps brakes well below 400 degrees Fahrenheit. Short track racing sees temperatures of 800 to 1100 degrees. Road course racing pushes rotors to 1400 degrees, hot enough to glow bright orange and throw sparks. NASCAR. Right front brake rotors routinely exceed 1500 degrees for 500 miles straight. These environments couldn't be more different, and brake compounds optimized for one cannot function properly in the other. This creates the most dangerous consequence of running racing brake pads on the street: poor cold bite performance. When you need maximum stopping power in an emergency, say when a child runs into the street or traffic suddenly stops ahead of you, racing brake pads operating at street temperatures may deliver frightening, inadequate stopping distances. The coefficient of friction that racing pads rely on simply isn't available when they're cold. Brake experts warn these pads shouldn't be used on the street because they require significant heat to work well, making them a poor choice for emergency cold stop situations. The noise factor alone makes racing brake pads unsuitable for street use. Racing brake systems aren't designed to be quiet, and significant squealing should be expected. These pads deliberately sacrifice noise reduction features found in street pads. In motorsports, measures like noise shims or insulating materials often get eliminated because they'd melt under extreme operating temperatures. The high friction formulation that provides racetrack performance inevitably leads to increased noise, even during normal street driving. One Hawk HP Plus user noted that these light track and autocross pads have great bite but come with noise. They're not intended to be a street-friendly, quiet pad. The rotor wear problem compounds over time. Racing brake pads become significantly more abrasive when operating below their designed temperature range. Not only do they wear themselves down faster in cold conditions, but they aggressively wear rotors as well. Higher metal content racing pads wear through rotors much faster when cold, creating unnecessary expense and maintenance headaches for street drivers. As the pads heat up toward their operating temperature, they become less abrasive, but street driving rarely provides sustained high-temperature operation. Brake dust from racing pads presents both aesthetic and practical problems. Racing compounds produce substantially more dust than street pads, and this dust often becomes more corrosive due to higher metallic content. The metallic brake dust can etch into an alloy wheel's protective coating, causing irreversible damage if not cleaned regularly. There's a common misconception that heavy, dark brake dust indicates powerful, high-performance brakes, but modern street-legal vehicles achieve excellent performance without excessive dust production. The inconsistent performance of racing pads operating outside their thermal range creates what experts call an on-off switch feel. A brake pad operating on the outer edge of its temperature range may behave completely differently from one corner to the next as it moves in and out of its optimal thermal window. This inconsistency makes precise brake modulation difficult and can lead to unexpected changes in stopping power mid-corner or mid-stop. Racing brake systems also demand different maintenance schedules that most street drivers aren't prepared to follow. Racing brake fluid, formulated for higher boiling points, has limited service life and must be flushed at least annually, regardless of mileage. Conservative drivers who track their cars more than 6 weekends per year often flush and bleed their brake systems before every event. DOT brake fluid reaches 3.7% water volume after roughly 2 years of use, and contaminated fluid can create a spongy pedal feel and reduced boiling point. The pad cracking and chunking issues that plague racing compounds in street use stem from thermal cycling stress. Racing pads experience repeated heating and cooling cycles in street driving, but these cycles occur at temperatures below the compound's designed operating range. This can lead to surface cracking, and in some cases, actual chunks of friction material breaking away from the backing plate. Raybestos racing pads have been particularly noted for cracking in street use applications. Rotor thermal cracking represents another failure mode specific to the temperature mismatch. Brake rotors typically don't crack from impact damage like hitting potholes. Instead, they fail due to heat-related stress and repeated thermal cycling. Every brake application causes the rotor to heat up and expand, and the large temperature excursions during hard braking can generate surface cracks or cause plastic deformation. High-performance rotors designed for racing applications may be more susceptible to thermal shock when subjected to the irregular heating patterns of street driving. The industry has recognized these compatibility problems and developed hybrid solutions. Companies now offer crossover compounds designed to bridge the gap between street and track performance. EBC's Blue Stuff material, for example, provides street-legal R90 certification while maintaining stable friction up to 1,000 degrees Fahrenheit, higher than street temperatures, but lower than pure racing compounds. These hybrid materials typically offer 30% longer lifespan than their racing counterparts while reducing noise and dust production. Carbon ceramic brake systems, while offering exceptional high-temperature performance, present their own street driving challenges. These systems can actually perform worse than traditional steel brakes in cold weather or during normal daily driving. While carbon ceramics can withstand temperatures exceeding 1,800 degrees Fahrenheit, they're also brittle and prone to cracking or chipping if not handled carefully. The high thermal conductivity that makes them excellent for racing applications can work against them in cold weather street driving. Professional recommendations consistently favor changing brake pads for track use rather than compromising with a single compound for both applications. This approach eliminates the performance and safety compromises entirely by running dedicated compounds optimized for each specific use case. Street pads provide quiet, consistent, cold weather performance with minimal dust, while track-specific compounds deliver maximum high-temperature performance when needed. The economics also favor the dedicated approach. While racing brake pads may seem like a performance upgrade, their accelerated wear rate in street applications, combined with increased rotor wear and potential thermal damage, often makes them more expensive in the long run. Factor in the safety implications of reduced cold weather stopping power, and the case for street-appropriate brake compounds becomes compelling. Understanding these temperature-dependent performance characteristics helps explain why automotive manufacturers spend considerable engineering effort developing brake compounds specifically matched to each vehicle's intended use. The brake system represents a critical safety component where compromise can have serious consequences, and the thermal environment fundamentally determines which friction materials will provide optimal performance. The allure of racing brake components is understandable. They represent the pinnacle of braking technology and offer impressive performance numbers. But those performance benefits only materialize within their designed operating parameters. Installing racing brake pads on a street car is like wearing racing slicks in the rain, the wrong tool for the operating environment with potentially dangerous consequences. The solution lies in matching brake components to their intended use. Street driving demands consistent, predictable performance across a wide temperature range, with emphasis on cold weather effectiveness, low noise, and minimal maintenance. Track driving prioritizes maximum high-temperature performance and fade resistance. These represent fundamentally different requirements that call for different solutions. For drivers who occasionally track their vehicles, the professional recommendation remains clear. Change brake pads for track events, then return to street-appropriate compounds for daily driving. This approach maximizes both safety and performance by ensuring each compound operates within its designed parameters. The small inconvenience of swapping pads gets far outweighed by the safety benefits and improved overall experience in both environments. The brake system serves as your vehicle's most critical safety component, and understanding the fundamental differences between racing and street brake compounds helps ensure you choose the right tool for your driving environment. When it comes to stopping power, there's no substitute for components designed specifically for the conditions you'll actually encounter. Make sure you subscribe.